Everyone, welcome to a lecture for section 2.3 on cylindrical shells. So this is going to be an alternate method, but it's going to compute the same volumes that we were considering in section 2.2. So just to kind of get an idea of the basic shapes that we're dealing with. If you have a function, let's say, let's consider about the y-axis. So if you have a function f of x, maybe say going from this. From A to B, and we're kind of bounded below by the x-axis, and we want to rotate this around the y-axis. Then basically what we're doing is we're just going to reflect it about the y-axis, and if I can draw this nicely-ish, whatever, you're going to kind of just create your solid of revolution this way. And what you want to do is you want to kind of pluck out from here a cylinder. So basically you just take a little bit of width on the x-axis and you just rotate that width around the y-axis. And then so what you have is just kind of a cylinder that's chunked out from this solid of revolution. And the idea is that this cylinder, we can easily compute its volume. By kind of cutting it down the line. So you kind of just want to take scissors and kind of just snip, snip, snip down this line. So what happens when you do that is you can unroll it. So think about maybe taking like an empty toilet roll and cutting it down lengthwise and then flattening it out, and you would have a rectangle. So what you're left with is a rectangle. And it has a little width to it. So the width we can see comes from here. So you have a little bit of width. So that's your width. So that's my width here. So this is going to be width. It's a little change in x. We can see it's a little width on the x-axis. So we're going to call that dx. And then it also has a height. The height comes from here, right? Where that height is actually given by the function line. So your height equals just the height of the function, which was f of x. We label that. So this guy here, whatever, this is f of x. And then you also have along the bottom is the length of your kind of flattened toilet paper roll. So the length is really the circumference of this circle. So the length is really just this guy here. So it's circumference. So it's 2 pi times the radius, where your radius is just the distance from the center of that circle out to a certain x value. So this is going to equal 2 pi times x. So the volume equals these three dimensions multiplied together. So you get 2 pi x times f of x dx. And so that's where the volume comes from in this formula here. So that's exactly what we have right here. So the only other thing really to kind of highlight is that you're only considering your cylinders when you're in this range, which is from A to B. So if you had a cylinder, say, starting in the between 0 and A, well, you're not really in the solid because that's a hole that's empty. There's no solid there. So let's try to do an example where we're given a specific f of x. So here we're going to have f of x equaling 1 over x, and we're going to bound below by the x-axis, okay, and we're going to be on 1 to 3, and we're going to go around y. So always draw your solid of evolution. So we know we're going about the y-axis. And if we're, let's see, 1 to 3, so 1, 3. I know I'm going to have to reflect this over the y-axis, so I'm going to go ahead and mark where these are going to be. So when x is 1, f of x is 1. And then when x is 3, f of x is 1/3. So I'm kind of just sloping gently down here. And then I'm bounded below by the x-axis, so I can extend these straight down. So this is my region here. And I'm going to rotate this about the y-axis. So in order to do that, I typically just draw the reflected region. And so this would kind of look like so that's your solid of revolution. And now what we have to do is we have to kind of figure out what our cylindrical shell looks like. So you just want to take from anywhere kind of in the middle just to give you an idea. The shell goes all the way down to the x-axis as well. Some people kind of call this like the onion method as well, because you can kind of think about how an onion is set up, where it's just like smaller and smaller layers going inward. So if you take this one layer of your shell or of your onion, what you're going to have is your cylinder over here. And we just need to figure out what the volume of this particular cylinder is. So again, we're going to have that. We have a little width here. So this little width comes from the x-axis. So this is going to be our dx. And then we also have our height. But the height also comes from just the function itself. So our height is just f of x. And then lastly, we have the length of this around, which we call circumference. So then our circumference it's just 2 pi times the radius. And so the radius is just x. So let's put it all together. we're going to have the integral, because again, we're adding up all these cylinders. So, you know, the fancy way to add stuff up is through integration of infinitesimally small objects. So our x values are from 1 to 3. And then we just multiply these three things, our circumference, our height, and our width. So it's 2 pi x times our function, which was 1 over x, and then times our little width, which is dx. So now I'm going to simplify the integrand. So I should get 2 pi dx, and this is also another really nice simple integration. So I just get 2 pi x, and I evaluate it from 1 to 3. So this is going to leave me with 4 pi. So here's another example that's going to be pretty similar. We're still going about the y-axis. We have a nice little function. This is like another bundt cake pan example. So again, start by drawing. We have our function given to us. It is 2x minus x squared, which I look at as 2 minus x by x. I do that because it helps me know where I'm going to plot my roots. So my roots are going to be at 0 and 2. So then I know I have to go out, say, -2. And then the vertex is always in the middle. So I'm going to be at 1. And when I'm 1, I'm 1. So 1 and 1. Okay. So you just have a parabola with the vertex at 1, 1. And then you're just going to rotate this around the y-axis. So what you get is kind of, well, what I tried to describe earlier, which is the bundt cake pan. So this is your salt of a revolution. And we want, again, to kind of suss out what our cylinders are going to be. So I would like to show maybe another way to draw this that's perhaps a bit less messy. So another way to draw this out is just to draw your parabola, or whatever your region is. Just whatever your region is, just draw it, then reflect it. And then instead of going through the trouble of drawing the whole volume or the whole solid of revolution, you can go ahead and just figure out what your cylinder is going to be from here. So maybe you do something like this. Right, so now you kind of just have your cylinder as it occurs naturally in the wild. And so all we need to do again is just figure out our 3 dimensions of this cylinder, determine all of our x values, and then go ahead and integrate. So first we're going to have, we know our radius here is x. We know that our height here is f of x, which was equal to 2x minus x cubed. And then we also have kind of this small little change here, which is our dx. So we can go ahead and put that all together. So I'm integrating from 0 to 2. And I have 2 pi x, because again, this is our circumference. And then I'm going to multiply that by 2x minus x squared, because this was our height. And then dx, this was our width. So I'm going to go ahead and simplify the integrand. 0 to 2, 2 pi times 2x squared minus x cubed dx. And then this is just a polynomial, so we can integrate this relatively easily. So I get 2 pi times 2/3 x cubed minus 1/4 x to the 4th. And I'm going to evaluate that from 0 to 2. So the fundamental theorem of calculus part 2 says I can just plug all this stuff in. So I'm going to get 2 pi times 2/3 times 2 cubed minus 1/4 times 2 to the 4th. And then if I plug in 0, I'm just going to get 0. So I'm not going to write all that out. Okay, so if we simplify this a little bit, we're going to get 2/3 by 8 minus 1/4 by 16. So 2 pi of 16/3 minus 4. So that would leave me with 4/3 and then times 2 pi. So this will give me 8 pi over 3. And that is the volume of the solid generated by rotating f of x around the y-axis. So now we can move on to thinking about rotating about the x-axis. And it's going to be the exact same idea, exact same setup, except that in this case, we're going to be in terms of y and dy. So of course, graph. So we're taking g of y equals 2 root y. And y goes from 0 to 4. And we're bounded on the left by the y-axis. Okay. So when x is 0, when y is 0, we should also be at 0. Okay, so we have y0, x0. Then when y is 4, x is also going to be 4. So that's the 0.44. So I'm here. And this thing should look like that. And then I'm bounded on the left by the y-axis and above by y equals 4. So my region is this guy here. And then I want to rotate this around the x-axis. So what's going to happen is I will just kind of reflect this. And then your solid is here. So now what happens is we have to figure out what our cylinder is, and we're going to do this the same way. So I just take a little slice here, and then I rotate that around the y-axis. Right, so that's my cylinder. And now I kind of want to just figure out what the volume of that particular cylinder is. So again, you don't have to draw the whole solid. You can just draw the cylinder within and kind of go from there. I like to be a little bit more judicious with my volume calculation, so I like to redraw the cylinder. So we're just going to have this little cylinder here. And then it's also good to kind of pay attention to where this is in space. So this is my x-axis. This is my y-axis. So now I need those 3 dimensions again. So looking at kind of the width part of it, I'm going from here to here. So notice that's a little change on the y-axis. So this is going to be dy versus when we had it oriented perpendicularly, that little sliver was a small change on the x-axis. So that's why it was dx. So the next thing we need to do is we need to figure out this length. So normally we would call this height, but whatever. So we'll call this length or height, dealer's choice, length it is. So the length actually just equals the function. So it's 2 root y. And then we also have to find the circumference of the whole thing. And the circumference is determined by the radius. So the radius here, it's just the how much we went from the x-axis to y. So that's just y. So now we can go ahead and put it all together. So the volume of this shell is given by, so just this shell, not the whole thing, is given by 2 pi y. So again, this is the circumference times 2 root y. So this was the length, formerly the height. And then we have dy, and this was the width. So now we're going to add them all up in our fancy way that we call integration. So where are we integrating over? It's changed a little bit. So before we were doing it along the x-axis, and now we're actually along the y-axis. So we can see that as our y, as we're really close to the origin, we're going to have narrow, short little cylinders, right? You're going to have a little cylinder here that looks like this, right? When your y is small. As we get larger, the cylinders become larger. And so you kind of think about that as going up the y-axis here. So we start at 0, we go to 4. Then we just take our volume of our shell, which was 2 pi y times 2 root y dy, and we can simplify the integrand and proceed as usual. Okay, so 0 to 4, 4 pi y to the 3/2 dy. So I'm going to get 4 pi times 2/5 y to the 5/2, and I'm going to evaluate that from 0 to 4. So I get 4 pi 2/5. I know that when it's 0, the whole thing's going to be 0, so I'm not even going to mess with it. I'm just going to plug in 4. So I have 4 to the 5/2. Okay, so here's how I do 4 to the 5/2 in my head. First, I do the halves part. So the halves just means square root. So maybe we'll just do this over here real quick. So 4 to the 5/2. So this is really 4 to the 1/2 to the 5th. So 4 to the 1/2 is the same thing as saying the square root of 4, which I'm very confident is 2. And I know my powers of 2, so I know that 2 to the 5th is 32. Okay, so what I get is 4 pi times 2 over 5 times 32. So 32 times 8 gives me 256. So this is 256 pi over 5. All right, so now we're going to kind of elevate the level of complexity. We're not going to rotate about an axis. We're going to rotate just a little bit off of an axis. So this next one, we're going to go about the line x equals -1. So it's still the same procedure. We just have to be a little bit careful with our radius, because previously our radius has been, okay, how far away from the x or y axis are we? And it's usually been just an x or just a y, depending on what axis we're rotating about. But now, since we're rotating about, you know, x equals -1, we have to kind of factor in that extra distance into our radius. But it's super straightforward. You just have to be organized in your diagram and in your thought. So always begin by drawing. Our graph is given by f of x equals x. We're bounded below by the x-axis. We're from 1 to 2, and we're actually going to go about the line x equals -1. So if I draw this out, so from 1 to 2, so here's my line, by the way, here's my function. So this is f of x equals x, and I just want to do it from 1 to 2. So I'm here, and then this is my region. So this is also 1, this is also 2. So here's my region. And I want to rotate this about the line x equals -1. So I'm rotating here. So that means then that I'm going to have this distance. It should start, if it started here, if I drew my guy here, I would have an asymmetrical distance on my axis of rotation, which is definitely not what you want to do. So make sure that you're giving enough space here. So we need to go out to -3 because we need to make sure that we have that same distance on each side. So I'm going to go up to 1 and then to 2. So this is what it looks like if I were to reflect it across the line x equals -1. And so what happens is, it's a bit high for my tape. So what happens is now your solid of revolution looks like this. So we want to punch out a cylinder from here. So I'm just going to take a little cross section from my original shaded region R, and I'm going to rotate it about the same line x equals -1. And so that's going to give me this cylinder here. So now you have your cylinder kind of chunked out of this solid of revolution. So what we need to do, I think this will be helpful. I mean, I always think it's helpful to me. Hopefully drawing it both in the solid of revolution and outside as well is somewhat useful to you as well. Okay, so here's our cylinder. And again, I want to orient it in space. So we have to be aware that the x-axis is coming in through here. Sorry, the y-axis is coming in through here. And that we're rotating about the line x equals -1. And this is where we're rotating. So if I wanted to find, so the height is pretty straightforward actually, so we can just start there. So the height of this guy is just given by the function itself. So the height is just x, right, which was f of x. And then we have our little width here. So our width is just a small change in x, so that's d of x. But now we have to, in order to figure out the circumference, we need to know the radius. So remember that the radius is starting from the axis of rotation. So that means I'm going, first I have to go to the y-axis, and then I'm going over here. So from the y-axis to this point, that's just x, like it has been before when we rotated just about the y-axis. But now we're always going to go this extra distance from -1 to 0. So this is 1. So notice that the radius equals x plus 1. So that's what's new. That gives us a circumference of 2 pi times x plus 1. So now we're ready to put it together and integrate. So we're going to get our integral. We're going just from 0 to 2. Sorry, we're going just from 1 to 2. So we get 1 to 2 of 2 pi times my radius, which is x plus 1, times my function, which was just x, times the width, which was dx. So we're going to get the integral from 1 to 2 pi x squared plus x dx. Integrating polynomial is no problem. So 2 pi 1/3 x cubed plus 1/2 x squared, evaluate from 1 to 2. And let's see, this is why I do this on paper before I do lecture, to make sure that all my numbers are correct. Thank you, Fabian. Okay. So, perfect. So we're going to get 2 pi. So 1/3 times, that's a cubed, times 2 cubed, plus 1/2 times 2 squared, oops, minus. So if I just plug in 1, cubing and squaring it doesn't do anything, so I'm just going to say this is 1/3 and a half. Okay, so I get 2 pi times, let's see, that's 8/3 plus 2, and 1/3 and a half together through addition is 5/6, so I'm going to subtract 5/6. So now I get, what do I get? 14/3 minus 5/6. So that should give me 23/6, and then I multiply that by 2 pi. So this should give me 23 pi over 3. So that's it. So that's about, that's rotating it about a line that isn't an axis. Okay. Further complicating things is considering maybe we're not bounded to the left or bounded below by an axis, like maybe we're bounded by another graph itself. So now we have two functions, f of x equaling the square root of x and g of x equaling 1 over x. And we're given an interval, and we're going to actually have kind of a more of a complex shape. So we're going around the y-axis again. And we're on the interval from 1 to 4. So for f of x, when x is 4, we should be at height 2. And then when it's 1, we should be at 1. So I'm here. So this is f of x equaling root x. And then we also have for g of x 1 over x, the point 1, 1, and then also the point 1 and 1/4. So this is 1, this is 1/4. So you're going to be down here. They're not both supposed to look like parabola-esque, but oh well. So here's my region. and I'm going to rotate this around the y-axis. So again, we just kind of want to reflect this over. So it should be looking like this, and then maybe like this, and then like that. Okay. So I'm not going to draw this all the revolution this time. I'm just going to draw the cylinder itself. So to draw the cylinder itself, I just take a little slice out of my region, right? This little bar. And then this is the thing that I'm going to rotate about the y-axis. So my cylinder looks like this. So that's my cylinder. And so to figure out what the volume of this cylinder is, we're going to have our radius r, which is just the distance from the y-axis to some point x. So it's very simply just x. And then we also have our little width here. So that's just dx, a small little change in x. And the thing that's different this time is the height. So the height here, it's just the distance from f of x to g of x. Maybe I should label g of x. So remembering that g of x is 1 over x. So our height is just going to be f of x minus g of x, which is root x minus 1 over x. So now we can put it all together. Remembering that we're integrating over this interval here. These are all the possible x values we can use. So we're going to go ahead and go from 1 to 4 of our circumference, which is 2 pi times the radius. The radius was x. Then we're going to multiply that by our height, which was f of x minus g of x. So that's the square root of x minus 1 over x. And then we're going to go ahead and finish it off with the width, which was dx. So now I can simplify my integrand, giving me 1 to 4, 2 pi, x to the 3 halves minus 1 dx, another straightforward integration. So 2 pi times 2/5 x to the 5 halves minus x, and we're evaluating that on the interval from 1 to 4. So this should give me 2 pi times 2/5 4 to the 5 halves minus 4 minus 2/5 1 to the 5 halves minus 1. Again, you don't really have to write all that out because we know that 1 to any power is just going to be 1. So we get 2 pi. Okay, so we said 4 to the 5 halves earlier was 32. So this should be 64 over 5. And I'm going to convert the 4 to 20 over 5. And then I'm subtracting 2/5 minus 1, which is 5/5. So this is going to be negative 3/5. Okay, so 64 minus 20, 44 plus 3, 47, and then times 2. So this should give me 94 pi over 5. Okay, so now we should really think about the kind of the benefits or the pros and cons of having these two methods. There are going to be times when it's up to you to decide what method you should use. And in those cases, you should, again, always draw your region and your revolution, because there's going to be instances where maybe using the washer method is a total pain. And there's going to be times when it's not even possible. potentially. So let's do two examples and we'll set them up both ways so we can kind of see the benefits of one over the other. So for the first guy, so we have the region bounded by y equals x, y equals 2 minus x in the x-axis. And by the way, these are all going to be about the x-axis. Okay, so for this one, so this is y equals x, and this is y equals 2 minus x. So our region is really here. And we're rotating this around the x-axis. So it kind of just looks like this thing here. So if we wanted to do, a lot of people think that the washer method is the easiest, so we can start there. So if we wanted to do a washer, your washers would kind of come into two forms. So you would have, let's say if I started here, I'd have a washer here. But there's also another washer, maybe say here as well, that's going to take on a different characteristic. So this washer here, and this is the line y equals x, and this is the line y equals 2 minus x. Okay. So this washer, its radius is given by the line y equals x. So this is pi x squared. But notice that the governing line, the governing function changes here. So this is the 0.1, this is the 0.2. So this washer over here has a different form. It's actually pi, and its radius is 2 minus x. So I have two different washers. So in order to set this up, I'm going to have to go first from 0 to 1 and use pi x squared. And then I'll have to have a different setup on 1 to 2 where it's pi 2 minus x squared. Right, so it's a little bit more complicated. We're not going to evaluate these integrals, we're just going to set them up. So let's go look then at the cylinder over here for the same region, but with a different method. So if I have my cylinder, I think this one's actually a bit easier because the cylinder is going to have, let me zoom in a lot. So the cylinder has, the radius here is just y. And the little tiny distance here, right? So that's going to be our width. This is just dy. And then you have the length. Which is just going to be the far right function, which is 2 minus x, minus the far left function, which is just x. So we have to be careful though, right? because if I'm going to be using dy and y, these really need to be in terms of y. So this is the kind of the little hinky part in this particular setup. I still like it better, but we just need to be careful. So we need to kind of make sure that if, even though I'm just rewriting this, this is just x equals y, right? Because the variables are the same. So this should have really been y. And then this one is the same as 2 minus y equals x. So in here, I should have written 2 minus y. It's not always as easy as just switching the variables, by the way. Like, let's say, for example, if I had y equals x squared, that's not the same as x equals y squared, right? These are not matching. One of them would have been square rooted. So just be aware of that. Don't just switch the variables. So now if I wanted to set up this guy to do the shell method, the onion method, the cylinder method, whatever, my volume is going to be, well, first of all, where am I integrating over? I'm integrating, before we were integrating over from 0 to 1, and then we had a different integral from 1 to 2, but that was where we were. In this one, we're just going to have it all in one piece. So we're just going from this point here. So we do have to know what the height of this is. It's 1, by the way. So we're going to go from 0 to 1, and we're just going to multiply these all together. So I have 2 pi y, which is my circumference. Then I have the length, which is 2 minus y, and then the width, which is dy. So this simplifies nicely. I'll just leave it as 2 pi y times 2 minus 2y dy. So I like the cylinder method better, or the shell method better, because it's just one integral. They're both fine. You can use both. There's no like penalty for choosing one over the other. In this next example, I think we'll make an even stronger case that one method is preferable over the other. So let's move on to example B. So this one is going to be given by the parabola y equals 4x minus x squared. We're still going about the x-axis. And now you're really going to see kind of what a pain in the butt one of them becomes. So this one is a parabola. So this is y equals, what is this one? 4x minus x squared. So when I'm at 2, I'm at 4. So you have a vertex here. And then we rotate this about the y-axis as well. So if we were to do, let's do the washer method first. I'm going to steal this and copy it so I don't have to rewrite it. So if we're going to do the washer method, then our washers are just going to be, they're always governed by the same function. So you just have a washer. There's no hole, so it's technically a disk here, but semantics. So here's our washer. So the volume of this washer is just pi r squared, and the radius is just given by y, 4x minus x squared squared dx. So if I were to set up my volume, I'm going to go from 0 to 4 along the x-axis, and I just get pi times 4x minus x squared dx, right? And so that's just a polynomial that we can easily integrate and evaluate. If I wanted to do the cylinder or shell or onion method, my cylinders would be like this. But notice that I'm going to have to kind of like subtract something to get the length. This is definitely a hasty drawing, I apologize. Whatever. So how would I get, like, it's pretty clear, right? Like, okay, fine. This is just dy. Your radius is just y. But what is your length? This is where it becomes really hinky, because now your length, you know, normally we would do like just subtracting the two functions, right? We would say, okay, well, the one on the right is f of x, and the one on, or is f of y, and the one on the left is g of y. So my length is just f of y minus g of y. And then, you know, my day continues as normal. Well, now I have this issue where it's really just given by one function. So what? So should I put f of y minus g of y? Well, that would be 0. That's insanity. So it would suffice to be like, no thanks, I'm good, I got my washer, I'll see you on the next lecture. But if you're like dying to know, this is what you could do if you were feeling particularly bold. So, okay. Okay, so if y equals 4x minus x squared, then you could write this into your like vertex form. So this is really y equals negative x minus 2 squared plus 4, right? Because your vertex is at x equals 2, so you subtract that off before squaring it, and then the height is at 4, and then, okay, it opens downwards, so I better make it negative in front. Fine. But I need to write, in order to do this, I need to write my function x equals something in terms of y. So now what I have to do is I say, okay, this is y minus 4 equals negative x minus 2 squared. Flip the signs on both sides, x minus 2 squared, square root the whole shebang, 4 minus y equals x minus 2. But wait a minute, if I square root, I get a plus and a minus. Okay, this is essential. So now adding a 2 to both sides, I get 2 plus or minus the square root of 4 minus y equals x. And this plus or minus action that we're doing actually gives us the two different curves. You know, I'm talking about f of y minus g of y. This is going to give us that. So the sneaky thing here is to realize that, okay, what fun color can we use? Sure. So if I were looking at this, kind of just redrawing it, there's kind of a divide here, right, at the vertex, which was, we said 2, 4. So this curve is given by x equals 2 plus root 4 minus y. And this guy is given by x equals 2 minus 4 minus 2 minus the square root of 4 minus y. So that's how we're going to get our two curves. Therefore, if I wanted to do the shell method, I would first have to convert my quadratic into vertex form, then solve it for x in terms of y, then make sure to separate the two possible functions according to where they are in their domain, and now I'm ready to go. So I get, weesh. Well, the good news is it's still one integral, but I'm going to go from 0 to 4. That's like all my possible heights here, right? This is my 0 to 4. Then I get, what do I get? I get 2 pi times the radius, which gives me my circumference, and the radius was just y. then the length is going to be the right side minus the left side. So I get 2 plus the square root of 4 minus y minus the square root of 4 minus y, and then times our little width, which was just dy. So even though this does simplify nicely, I would still classify it as like a pain in the butt problem. Like I would much rather, like we would just be done by now if we had done washers, you know what I mean? So, okay, so we get 2 pi y, these twos cancel, and then I get times 2 root 4 minus y. Okay, so then if I, okay, even further, if I wanted to integrate this, which I don't, by the way, I would have to do a u sub on the radicand and then go forward. I mean, I can't overstate enough how much of a pain in the butt this problem is. So, okay, that's my sales pitch on making sure that you consider your options before committing to a method. There are going to be times on the exam or in the homework where I say, hey, set up the integral using shell method or set up the integral using disk method. And there are going to be other times where it's like, use whatever method you want, just integrate it and tell me what the volume is. So in the latter, it's up to you to decide which is going to be better. And don't be surprised, wink, word to the wise, write this down, put it in your calendar, text a friend, word to the wise, don't be surprised if we see an example like this, the very last one we did, the pain in the rear problem. If we see an example like this on an exam, and I don't tell you to use shell or washer, I just say, hey, make it happen. So that's it. That's all I have for this lesson. Good luck. Definitely email me or post to the forum if you have any questions or if you see any typos. I've already been busted once this week and class hasn't even started. So good luck to you, and I'll see you soon.